So let's now try to do a more sophisticated example of determining the Fourier series coefficients. So in particular, for this example, we're required to find the Fourier series coefficients of the square wave. This is a discrete time square wave, and which has a period of capital N. So unlike the previous example that we saw, we will not be able to use Euler's identity, of course, here. So we'd have to resort to determining the Fourier series coefficients by using the analysis equation. Let's try to do that. So I know from the definition from the synthesis from the analysis equation that the Fourier series coefficient a sub k is given as 1 upon n summation over k, where this k can be any interval x of n e raised to power minus j k times 2 pi by capital N times n. And to make my life easier, one of the things I'm going to do is that I will choose this. So this summation is over n. So in order to make my life easier, what I'm going to do is I am going to sum not from 0 to n, but rather, and that's something I could do, but maybe a better approach, which makes things easier, is to sum from over here to over here. In other words, from minus n by 2 to plus n by 2, assuming n is odd. If it's assuming n is even, if it's odd, it would be just one sample shifted. Nevertheless, so if I sum from minus half of the period to plus half of the period, I'd see that the signal is 0 for all of the indices except from minus n1 to plus n1. So this therefore is equal to 1 upon n, and where the summation goes from n equals minus capital N1 to plus capital N1. And for all of the indices of n within this interval, I know that x of n equals 1. So that's just 1 here, which I don't really care about. And this is e to the minus j k 2 pi by capital N times small n. And this, therefore, is just a simple finite series relationship. But let me elaborate on this a little bit further anyway. So if I make a change of variables, so if I say that m equals k, so m equals small n plus n1, and then I see that when small n equals minus n1, m is going to be equal to 0. So I bring this finite series sum into a standard relationship that we're familiar with. So this becomes equal to 1 upon n, and the summation now is going to be over the new variable, which is small m. And over here I have e raised to minus j k 2 pi by capital N, and small m, n is small m minus capital N1. On the other hand, what about the summation limits? And we see a small n being equal to minus n1, that makes small m being equal to 0. And when this is n1, this becomes equal to 2n1. So the summation really goes from 0 all the way up to 2 times n1, and so this is equal to e raised to power plus j k 2 pi times n1 divided by n divided by capital N, and this is multiplied by a summation, which is m going from 0 to 2n1 e raised to power minus j k 2 pi by capital N times m. And now I can just directly use the finite series formula, and this becomes equal to e raised to power j k 2 pi times n1 divided by small n. And here I have 1 minus e raised to power minus j k 2 pi by capital N. And in the numerator, I have 1 minus e raised to power minus j k 2 pi divided by N times the number of terms that I have in the summation, which are 2 times capital N 1 plus 1. Now, if you leave these, so these are the AKs. So these are the AKs. If you leave these coefficients as they are, it's not really a big problem because we've reached the correct conclusion. However, we can simplify this a bit further by manipulating these this numerator and the denominator. So it turns out the numerator divided by the denominator is actually a some sinusoid divided by another sinusoid. In order to do that, so let me elaborate this. So and highlight what the steps are going to be. So this is e raised to power j k 2 pi n1 divided by n, which I had earlier. And in order to make something like this, this a sinusoid. So if this is e raised to power minus j theta, let me just take half of this term outside. So this one is going to be plus j theta by 2, and this is going to be minus j theta by 2. So theta here is this thing here, k times 2 pi by n to n 1 plus 1. So all I want to do is I want to so take out as common, which is e raised to power minus j times this term divided by 2. So that term is e raised to power minus j k 2 pi by capital N times n1 plus half. And therefore, what I have on the inside is e raised to power plus j k 2 pi by n n1 plus half minus e raised to power minus j k 2 pi by n n1 plus half. And you'd see this is more, we're getting to an equation which looks like a sign. What about the denominator? For the denominator, I have, let me take the half of this term outside as well. So this is e raised to power minus j k pi by n, which is something that I take outside. This is times e raised to power plus j k pi by n minus e raised to power minus j k to pi divided by n. So let me correct this. So this is pi divided by n. Now what I observe is that this multiplied by this divided by this is actually equal to 1, and that's really simplifies the expression a lot further. So so really see this is 2 pi n1 by n. This is minus 2 pi n1 by n. So this is going to cancel out with this. This half is going to result in e raised to power minus j k pi by n, which is going to cancel with this term here. So our really so this cancel all of these terms cancel, and what you have inside these brackets, this is 2j times sine of this. This is 2j times sine of this. 2j is going to cancel with this 2j, because of which the relationship that we're going to get is ak is equal to sine 2 pi k times n1 plus half divided by sine by k divided by n. Now, one of the things really that we need to be careful about is that this relationship in fact holds true only when k is not equal to 0, because when k was equal to 0, what you'd actually get is the numerator turns out to be 0, the denominator also turns out to be 0. You could apply L'Hopital's rule if you wish to, but there's a much easier. So this relationship is only true for k is not equal to 0, within, of course, the interval 0 to n minus 1. And instead of applying the L'Hopital's rule in order for me to determine what A naught is I just simply go back to this relationship, which is the synthesis equation, and I just see that a naught is actually equal to 1 upon n summation of n from minus n1 to plus n1. Of course, the signal is 1 inside this interval, and this when k equals 0, this not only is this 1, this term is also equal to 1 because k equals 0. So what you're really summing is 1 how many times to n1 plus n times. So this is 2 n1 plus 1 divided by n. So the conclusion is, or the solution, final solution is that a k are equal to, within the interval, of course, from 0 to capital N minus 1 for values of k, this is 2n1 plus 1 divided by n when k equals 0. And otherwise, for non-zero values of k, this is sine 2 pi k n1 plus half divided by sine pi k divided by n whenever k equals 1, 2, all the way up to capital N minus 1. And one of the things you can verify now is you just take some value of capital N, some value of small n1, and it would be easy to implement in MATLAB. You use these coefficients here and try to uh, try to build the try to implement the synthesis equation, and you would actually be able to verify that when you do add up the complex exponentials, um, capital N of those appropriately scaled by these coefficients that we've determined, you are going to indeed get the square wave.